Now see a vibration of a spring in vertical direction. Suppose you have taken a spring, like this is a suspension point, one spring is here having natural length L and no mass, spring also is massless, assumed to be massless. So, there is no extension. Now, when a mass m is attached at the end, this mass m has got weight mg, because of this downward force acts. So, spring gets elongated and a vertical force act upside, that is called a spring force, that is equal to minus KL if here L is the elongation. Now, when this spring is pulled downward by a small displacement y, then now net restoring force acting upside is minus k into L plus y. Now, we can imagine this situation first. In equilibrium, we can write KL is equal to mg. So, K is equal to mg upon L. So, now see here, in equilibrium K is equal to mg upon L. In the here the third case, when the spring is pulled down by a displacement or by a distance of y, this spring start oscillating about this mean position. This is the mean position here, suppose. So, position of this equilibrium position here. So, the net restoring force acting here, we can calculate F net is equal to minus k into L plus y minus KL. We can calculate, it is here minus KL minus KY plus KL cancel. So, F net is equal to minus k into y, that means F net is directly proportional to minus y. It means net restoring force which is acting vertically upward directly proportional to negative of the displacement. So, here F net is directly proportional to negative of the displacement. It means the motion of the spring or the mass is here, that is actually simple harmonic motion. So, we can write here F is equal to, so this is time period is equal to 2 pi under root of m upon k, but already value of k we have calculated in the equilibrium position, that k was here mg upon L. So, we can put the value of k. So, getting 2 pi under root of m upon mg into upon L here, this is cancelled. So, t is equal to 2 pi under root of L upon g, or we can write frequency is equal to 1 upon 2 pi under root of g upon L.